A world time zone map looks like someone tried to slice Earth into neat vertical strips, then changed their mind everywhere. Borders zigzag around states, islands, rail lines, and communities, while some clocks sit 30 or 45 minutes off the hour. That is not a broken system. It is what happens when astronomy meets law, transport, and daily life. Start with the clean part. Earth turns, and the sun reaches its highest point at different longitudes at different times. Move 15 degrees east or west, and local solar time shifts by roughly 1 hour. If every town set noon from its own sun, every longitude could keep a slightly different clock. That was manageable when travel was slow and most schedules stayed local. But precise mechanical clocks, telegraph signals, and expanding railways connected places faster than their local times could agree. A timetable became a conversion puzzle, and a station could display clocks that contradicted one another. In 1883, American and Canadian railroads replaced that confusion with a small set of operational time zones. 4 continental zones let distant stations schedule the same train without translating dozens of local noons. Cities and governments adopted the railway pattern, turning a transport solution into civil time. Britain had already made Greenwich Mean Time its legal standard in 1880 after railways spread it across the country. In 1884, an international conference recommended the Greenwich meridian as longitude 0 for a shared global reference. That gave the world an agreed starting line, but it did not force every border into a perfect grid. The classroom model is elegant: 24 hours, 24 bands, each centered on a meridian 15 degrees apart. Cross one ideal band and move the clock exactly 1 hour. That model explains the geometry, not the political map printed in an airline magazine or stored in a phone. Real boundaries bend because a clock is a coordination tool, not a painted longitude line. A government may keep a state, trading region, or transport network on one clock even when the sun suggests 2. The result is less geometrically pure, but often easier for people who work, travel, and govern together. The United States makes that trade-off explicit. The Department of Transportation oversees zone boundaries because time standards serve transport. Federal law defines 9 zones and tells officials to consider commerce and carrier junctions when drawing their limits. So a boundary can follow a county or practical travel pattern instead of the nearest ideal meridian. Even the offsets refuse to stay on whole hours. India anchors its standard time to 82.5 degrees east, producing UTC plus 5 hours 30 minutes. That half hour is not an error. It is the chosen national relationship between local clocks and the global reference. Nepal goes another step. The current IANA rule for Kathmandu is UTC plus 5 hours 45 minutes. Quarter-hour offsets show why a zone cannot be reconstructed from longitude by rounding to the nearest hour. You need the actual civil rule chosen for that place. Lord Island adds a different twist. Its standard offset is 10 hours 30 minutes ahead of UTC. Its recurring daylight saving rule advances the clock by 30 minutes, not the more familiar full hour. One place can therefore combine a half-hour base with a half-hour seasonal change. All of these local choices need a stable comparison point, and that role belongs to coordinated universal time. UTC is the internationally agreed world time standard. Local time is expressed by applying a zone's offset and rules. Greenwich remains the zero meridian reference, but modern UTC is a coordinated time scale, not simply a town clock. Daylight saving is another layer, and it is often confused with the zone itself. UTC does not jump forward in spring. A jurisdiction changes the offset used by its local wall clock. In the United States, states can opt out, while participating states must follow federal transition dates. Move a local clock forward and some wall clock labels never occur that day. Move it back and a label can occur twice, even though UTC continues forward without repeating. Software must know the place, the date, and the applicable rule, A bare abbreviation or fixed offset is not enough. That is why computers use the IANA time zone database rather than a single frozen map. It stores machine-readable histories and future rules for representative locations, such as America, New York, or Asia, Kathmandu. A database zone is for clocks that agree, not a polygon tracing every road and county line. The database focuses on reliable behavior since 1970 because older local practices are harder to document consistently. Even historical transitions may be revised when maintainers find better evidence. That uncertainty is recorded instead of pretending every clock change in history is perfectly known. The database also keeps changing because governments keep changing civil time. Authorities can move a boundary, alter an offset, or rewrite daylight-saving rules with little notice. Your operating system therefore needs time zone updates for the same reason it needs other current reference data. A perfectly straight map would be simpler to draw, but it would force more communities to live by inconvenient neighboring clocks. A purely political map would ignore the solar rhythm that made longitude useful in the first place. The working system sits between them, regular enough to coordinate globally, flexible enough to serve local decisions. So why are time zones so messy? Because the sky supplies a reference, while people decide how clocks should organize life. Railways demanded standardization, Greenwich supplied a zero line, and governments kept the authority to bend the result. Subscribe for the hidden reasons behind ordinary systems, including the date line where the calendar itself changes sides.